Presentation for Agitation project. Group 15 confirmed by Caterina Herrera, Maria Camila Rodriguez, Laura Alejandra Rodriguez, and Daniela Suspes. Mixing and agitation are units of operation that are present in the majority of industrial processes. These operations involve one or several phases, and they can be done in the static mixers and heating systems. Additionally, they have different industrial purposes, such as homogenizations of bases, improving contact between reagents, air dispersion, heat transfer increasing, leaching of solids, and many others. In general, the success of the mixing operation depends on an appropriate design of the internal elements and mainly on the type of impeller used. The impeller dimensions that were used for this project were adhered to the restriction established in the project statement. The bleach blade turbine was designed based on the purpose of the thrusting impeller given in the statement, in order to do an exhaustive comparison between both of them. Furthermore, the physical properties that were used were constanticity of 1000 kg per cubic meter and a viscosity of 0.001 pascals per second. The tank and rostering impeller were designed in Autodesk Inventor in order to satisfy the requirements. Additionally, the parts were assembled with help of the given indication in the video that was posted in the support file. The rostering impeller can be appreciated. This impeller has 51 mm of diameter, where the disc has 33 mm, the blades have 12.5 mm and 10.4 mm of height. The tank was a standard tank with 4 baffles. Besides, the pitch impeller chosen was designed with the same diameter and the same tank dimensions. The design of these impellers can be seen in this slide. Furthermore, a bibliographic search was made with the purpose of finding an appropriate impeller that fulfilled the objective of generate a greater shear stress than rostering impeller. With this in mind, the pitch blade turbine impeller was designed in Autodesk Inventor, because it was found that the average shear rate was higher for the standard 45 degrees impeller. The K-omega turbulent model was used to predict the flow pattern, because this is the most complete method that realizes the dispersive energy per volume and time unit. This model is described by the following equation. Additionally, the torque, the time step, and the total time was calculated. Here, there are the results that we obtained. In order to create the mesh, the following steps were performed. Firstly, in the geometry file, the mixer and tank parts were selected. Secondly, the operation automated mesh was selected. In the window Create Automated Mesh operation, the surface measure, polyether measure, and prints layer measure were selected as meshing models. Thirdly, the condition mesh that was proposed in the project was used. However, the number of cells did not fulfill with the established range. Hence, the minimum base size was changed to 0.5 mm and the base size used was 2 mm. Finally, the number of cells was 429,000 for the pitch turbine. This number forms part of the range established in the statement of the project. On the other hand, 499,000 cells were obtained with meshing the rostering turbine, which is an ideal number if it is compared with the recommendation previously mentioned. In addition, it was not necessary to change the initial measured conditions. In this graph, it can be appreciated that power number depends on the Reynolds number. For laminar regimes, this value is higher, although it decreases substantively. On the other hand, for torsion regimes, the magnitude of the decreasing slope is smaller. Finally, for tubular regimes, this value is practically constant, but higher than in transient regime. Additionally, power number depends on the geometry of the turbine. Notwithstanding the same dimensions and parameters for the turbines, in a specific Reynolds number, this value is different for each one. In the laminar region, the power number obtained with rostering is slightly superior to pitch turbine. Otherwise, in transit section, this value is similar for both impellers. Lastly, the power number is higher for pitch than rotating turbine in turbulent regime, which implies that more energy is required mixing with impeller design in this section. Supplementary, it can be said that rotating turbine results are coherent. This is because the power and the power number obtained are similar to the theoretical values. Furthermore, values of error percentage are represented in a range delimited by 40.51% and 23.53%. For pitch impeller, it can be appreciated that turbulent and transit regimes generate similar results between the power number obtained by CFD and theoretical behaviors. On the other hand, for laminar section, the power number obtained was higher than the standard values. Maximum value on CFD was 77, and according to literature, this value must be 50. As it can be shown in this graph, the shear stress is directly related to the Reynolds number. Furthermore, this simulation demonstrates that the shear stress increases as units of viscosity, moreover, in turbulent regimes. This makes sense because the mathematical definition of shear stress, where the deformation speed is proportional to the stress. Additionally, it can be seen that rotating turbine generates shear stress values considerably higher than pitch turbine. Therefore, it explains why this type of impeller is strongly used for gas-liquid and liquid-liquid dispersions. It can be shown too that the power number is independent of the fluid viscosity. This is consistent with the mathematical definition of this number that related the power, density, rotational speed, and the diameter of the impeller. This means the proportion between the external forces and the inertial forces per unit of fluid volume. Finally, it can be concluded with the simulation that was made in the star CCM Plus. It was possible to determine that the proposed impeller fulfilled the objective. From the power number, it could be determined that the pitch blade turbine needs less effort to control the friction generated by the fluid than the rotating impeller. In addition, the comparison between two fluids with different viscosity is shown that this value is proportional to the shear stress. Besides, that it could also be observed that the power number is independent of the viscosity, but it depends strongly on the geometry used. Hereafter, it can be observed the animations obtained in different regimes for both turbines designed.